Now that we've talked about air pollution and acid rain, let's talk a little bit about our ozone layer and why it is so important, and how we humans have contributed to the destruction of the ozone layer, and what has happened since we've observed that the ozone layer is being destroyed. So the ozone layer is right above our troposphere, down here. And you can see it's about 20 miles above where you're standing right now. And it's a very important layer in preventing UV light from, in preventing an excessive amount of UV light from hitting Earth. So that is an important element to our health and safety. So having too much UV is bad for you and damages your DNA and can cause a lot of negative things to you and other organisms. So I mentioned this before, but it's important to distinguish between the ozone layer, which we consider to be very good and beneficial for our health. So that's up there 20 kilometers above above where you're standing now. I think I said 20 miles before, but regardless, it's a significant amount, significant distance above you. So there's our ozone layer up there. It's showing you 20 kilometers above where you're standing. And then right down here in the graph, at a much lower altitude, they're showing you the bad ozone. So when we talked about pollution, ozone pollution, in our previous video, we were discussing ozone that was the result of industrial processes that was producing ozone lower down, close to where the air you are breathing. So that would be considered. That would be considered ozone pollution, and you can see that it's at a very different layer than the ozone layer that we are going to be discussing now, that we consider to be beneficial to us. So the ozone in the stratosphere, that higher layer of ozone, protects you from UV radiation, and UV stands for ultraviolet. So here's a map of where the ozone is distributed, and ozone kind of flies around. So it gets produced a lot at the equator, and then or around the equator, and then it just gets moved around by, I guess, wind and air pressure, and it kind of accumulates at the poles. So you can see that there's more ozone at the higher levels of longitude, and a little bit at the lower layers. So this is a map showing you where ozone is distributed over our planet. Here's another map showing you how ozone is distributed. So the stratospheric ozone exists about 45 to 60 kilometers on Earth. A little bit of a discrepancy, but that's okay. It's all the same as far as we're concerned. And ozone absorbs UV radiation. So there's a lot of UV radiation coming in from the sun. Plus, the ozone is filtering a good amount of that. Filtering all of that UV light is enabling us to live, and actually with a much higher amount of UV radiation coming to Earth, our DNA would mutate much more rapidly, and life would be a lot different than it is now. So this is another map of the ozone distribution. They're showing you in the darker blue areas, so down here, that this is where the density is highest. And then there's also some lesser levels in these green and yellow regions, and then the levels are quite low right here in the middle by the equator. So this is not very critical for you to understand. We've been talking a lot about chemical reactions, and the formation of ozone is another chemical reaction. So, and this occurs in that ozone layer where ozone is. So we have oxygen, and sometimes these molecules break apart in the presence of UV, actually. So UV here is breaking bonds, just like it breaks the bonds in your DNA molecules. And sometimes that produces 3 oxygen molecules coming together instead of just 2. So around 1985, scientists observed that there was a decrease in the ozone layer above Antarctica. And here's a map showing you that decrease. So here's a satellite picture from 1979. So the more purple and the more blue areas are showing you a depletion of ozone in that area. So red means higher ozone, blue and purple means less ozone, and they're showing you from 1979 to 2005 that there was actually a pretty big difference in the amount of ozone in that pole. So those are just 2 years. Here's a lot of additional data from NASA. So they're getting satellite images of the ozone distribution in that area, and you can see earlier on we have a lot of those red. So here's the color map down here. It goes from red to purple. So red means there's more ozone. Down here purple or even black means that there's a lot less ozone. So here we have some nice red regions, and then we can see that there's been some pretty dramatic differences in the amount of ozone available. We also do see that there is fluctuations. So some years, for example, this year right here is not as bad as some other years. So there is some ebb and flow when it comes to the ozone layer. It is changing around. But if we graph it on a graph, we do see that consistently there's been a decrease in the amount of ozone that we see in the ozone layer. So here's more ozone is up here, less is down here, and we see if we just follow this graph with a straight line how it's been decreasing over time. And this goes up until 2005. So what is really encouraging is that that humans have taken precautions against producing molecules that deplete ozone. And because of these precautions, because we've been producing less of these chemicals, we actually see in this graph that goes beyond 2005 to more recently that the ozone layer is starting to recover. So when we see the thickness that it was back in the 60s, it was about 300, and by the 90s it went down to about 150. But more recently it's starting to recover a little bit. Now maybe it's around 175 or 200. So hopefully over time it'll just improve and get back to the level at which it was, which is a very optimistic demonstration that humans can alter their behavior and alter their industrial practices and even economic practices, right, their business practices, to come together and do something beneficial for humankind, such as rebuild the hole in the ozone, which benefits everybody on Earth. Okay, so how did we create the hole in the ozone? The biggest culprit were these molecules that were called chlorofluorocarbons, and these molecules were used in refrigeration and air conditioning as a propellant in aerosol cans. So hairspray is kind of the typical example people like to give. So any kind of hairspray that has that propellant. And blowing agents, which inject air into foam products like styrofoam. So these were big businesses, right? These were multi-billion-dollar businesses. And what's interesting to me is that, we talk about affecting change and what kind of economic downfall that might bring about, for example, car companies, right? So if we move away from fossil fuels, is that going to affect car companies, or is that going to affect the oil industry? So here's an example of multiple industries that were producing these refrigeration compounds and aerosol cans. And you could do a study of how they were impacted economically, but the point is that I think they adapted to regulations which said you may not produce, or not you may not, but we agree not to produce these chemicals anymore because we see that they're having a very detrimental effect on part of our atmosphere, which is really important and beneficial to us. So So these CFCs, these molecules, so let's say you use some hairspray, you spray your hair, the molecules stick around you for a while and then they float away and they move up into higher and higher levels of the atmosphere, and they'll actually go all the way up to those dozens of kilometers above Earth to the ozone layer. And they might take actually up to 8 years to get there. So they'll take their time, but they're going to stay the way they are and just keep moving through the air until they're all the way up there. Once they're there, these CFCs are going to start attacking the ozone molecules and breaking them apart. So they're going to chemically react with ozone and reduce it back down to oxygen. And what's a bit unfortunate is that so if you spray your hair, these molecules take 8 years to get up to the ozone layer, and they can stick around there for 200 years. So because of this, humans have modified their behavior with regards to producing these chemicals quite a while ago. However, there's still a lot of chemicals up there that were from a lot of housewives in the 60s blowing Aquanet into their enormous hairstyles. But over time they will degrade and go away, so that's the good news. So one chlorine atom from one of these CFCs can catalyze the breakdown of as many as 100,000 ozone molecules before it leaves the stratosphere. So this is how a small amount of these CFCs can actually stick around there for a long time, destroying ozone for dozens to hundreds of years. So the CFC, once it gets up to that stratosphere where the ozone layer is, there's a lot of UV radiation there. The UV radiation breaks off a chlorine from that CFC molecule, and that chlorine atom is going to go around breaking the ozone molecules. So we saw previously that there was a reduction in the ozone layer, and the ozone concentrations have decreased by more than 10%. And we saw that big dark hole in the pole, in the Antarctic pole, that where ozone has depleted the most. And ozone blocks these UV rays that come to Earth. So by decreasing the amount of ozone that we have, we've increased the amount of UV rays that reach us, and specifically we've increased the amount of UVB. However, let's look at some data from Our World in Data, which is a resource that I highly recommend you go look at. They have wonderful interactive graphs that you can play with. So let's look at this graph here. So we're looking at latitude on the x-axis across our planet, and here we're looking at the change in UV irradiation that gets to Earth. So we're looking at different wavelengths of UV. So the shorter a wavelength of energy, the shorter the wavelength of light of UV radiation, the more destructive it is, typically. So it's showing you, it's breaking down the different UV radiations and how much more we're getting now that this ozone is gone. We actually see in some regions, let's say right here where the hole in the ozone is, we're getting almost a third more UV radiation coming through. Closer to the equator, maybe the difference isn't as stark. However, if we go back again to the other pole, we also see somewhere in the range of more than 5%, or around 10% of UV radiation is coming through now that wasn't getting through previously. So this is comparing the present status to, or the 2008 status to the 1979 status. So now we have a quantitative measurement of how much UV radiation is coming through that was not coming through before. And what does excess UV radiation cause? So I've mentioned several times already that it causes damage to your DNA. And when UV radiation hits your skin and is breaking the DNA in your skin cells, this can actually cause them to become cancerous at some point. You might become very unlucky, and the UV radiation is going to cause some DNA damage in that cell that the cell is not going to be able to repair, and it will actually cause them to become cancerous. So here they're showing you in this graph the incidence of the increased incidence of skin cancer that might happen because of ozone depletion. So in green, so these on the y-axis here are the estimates of skin cancer incidence per million people. And if we look at the scenario where we didn't restrict any ozone depleting substances over time, so these agreements happened prior to 2000, but if we had not done anything at all, the incidence of skin cancer would have increased very, very dramatically. If we looked at the amount of CFCs that are produced according to the Montreal Protocol, which was a multinational agreement where a lot of countries came together and agreed to stop producing these chemicals that cause the hole in the ozone. So we're looking at a reduction compared to having no restrictions whatsoever in the incidence of skin cancer. However, it's still going up. And then here's another agreement that occurred where the restrictions were even more severe, and we can see here that ideally there would be no change to the incidence of skin cancer whatsoever. So this is just showing you that we can scientifically try to predict to the best that we can the amount of damage that anthropogenic activity is going to have on the environment, and this caused treaties between countries to come together and to implement changes in our behavior, implement changes in our industrial practices, and that was very beneficial to mankind. So that was a very good way to prevent the amount of UV rays hitting Earth, prevent the amount of skin cancer incidence that's going to happen, and furthermore, UV also affects a lot of other organisms. So it affects plants, it affects microorganisms, plankton, and things that are at the surface of the ocean. So UV can't penetrate very deep in the water, but it does hit a lot of organisms at the very surface. So we know that excess UV radiation is going to reduce phytoplankton growth in the ocean. So phytoplankton is an important part of the ecosystem, and you have already learned about primary producers and why those are so important for the ecosystem. So once humans saw the hole in the ozone and realized what an important impact this was going to have on health of the human health and the health of the planet, they signed an agreement in 1987, and you might recall that they originally noticed the hole in 1985, so that was a pretty rapid turnaround, right? 2 years to realize what from the observation to realize what was happening to actually taking action and signing an agreement to stop. Probably took several more years to actually ramp down production, but over time, actually they stopped producing these CFCs, and hopefully they are not being produced in most parts of the world anymore. So here's the Vienna Convention. This is the multinational agreement of people to stop producing products that contribute to ozone depletion, and they're showing you over time how many nations joined this agreement. So not everyone joined at once, but over time many different nations signed on to agree. There is some controversy more recently where it seems like CFCs are still being produced, and it's not very clear what country they're coming from. Someone seems to be breaking the treaty, which is unfortunate, but by and large, most people are respecting it and not producing these chemicals, and the ozone layer is improving. So let's take a look at some of that data. Here is the effect of the protocol. So once again, like the graph we saw previously, we can estimate what the impact is going to be of not taking any action at all versus taking action. So here we're looking at the amount of chlorine that we might have in the atmosphere, and if you recall, chlorine is the molecule, once it comes off of the CFC, that is going to start attacking those ozone molecules and converting them back into oxygen. So in the black line, that's the amount of chlorine that we'd have in the stratosphere that we'd see if we took absolutely no action. And then here are the various treaties that we had over time. Again, the first one in 1987, and then another one in 1990. More people signed on, more strategies were implemented, more guidelines and rules were implemented. Then we go to 1992, 1999, Montreal in 2007, and we can see that in that red line there, we're actually managing to decrease the amount of chlorine in the stratosphere pretty effectively by these negotiations and agreements that protecting the ozone layer is going to benefit everyone, not only health-wise, but also financially, ultimately. We can actually quantify the amount of ozone-depleting substance emissions. So in the red line are human-caused sources of ozone-depleting substances, and the blue line are natural sources of ozone-depleting substances. So, like we said, there are volcanoes and fires and other natural occurring elements that cause air pollution and ozone destruction. But happily, we can see that around 1990, when all of these treaties were signed, the number of ozone-depleting substances are dramatically reduced. So that is very optimistic. And our consumption of ozone-depleting substances is greatly reduced. So, these graphs mimic each other quite well. So we would hope that because we stop producing ozone-depleting substances, and we stop consuming ozone-depleting substances, that the hole in the ozone is going to improve. So here's the measurement of the ozone hole area, and we can see from 1979, so the graph is setting 0 to be the starting point, artificially setting that to be 0. And from 79 to 1990, the hole got much, much bigger, and then kind of stabilized. So we can see around now the hole is not significantly smaller. We do know that there is that the ozone layer is kind of starting to improve itself. We saw that graph before where we saw more ozone. However, we also have to keep in mind that these restoration strategies take time. So if you recall, we said that one of these molecules can stick around, one of these chlorine molecules can stick around in the ozone layer for 200 years, and continuing to cause damage. So it's going to take some time. It's going to take much longer than, it's going to take some time to actually restore that ozone layer and that hole in the ozone back to its original status. And that's why it's important to take these actions earlier on, because the ramifications continue on much longer than the time it takes to realize what's going on and to fix it. So if we all stop driving cars that use gas, right, in one day we magically all stop driving cars and stop contributing to air pollution in that sense, there's still going to be decades of continued damage that's being caused by all of the emissions that happened until that point. So, but the ozone layer is being improved and is being fixed. Ozone levels are being improved. Here's a graph of ozone concentrations previously, and then there's some projections into the future. So if we look at the blue line, we see the Antarctic, and that's where that big hole is. That big hole in the ozone is, and we can see we're kind of at the peak, but we are moving towards an improvement. So we're about here, and hopefully over the next 80 years the levels will restore, or 100 years, the levels will restore themselves to almost the levels that we started out with. which would be a great human accomplishment and a demonstration of our ability to implement strategies to reduce the harm that we're causing. This is a demonstration of the comment I made before, that it seems like despite this agreement that we have, this global agreement that we have that we're not going to produce these CFCs, it seems like some country or countries are doing it anyway, so there is some evidence that CFCs are continuing to be produced. So hopefully we'll get to the bottom of that at some point. So, this was a story of air pollution that humans caused without knowing that this would have such a detrimental effect on our atmosphere. So nobody thought that hairspray would be such a toxic thing to us and would cause skin cancer. I'm sure that nobody in the 50s or 60s could even possibly think that. And once we realized that how detrimental these things were to the environment, we took precautionary measures and active measures to stop producing them, and we can see the benefits of altering our behavior. So to reduce ozone depletion in the future, we have replaced HCFCs with CFCs, and most things use HCFCs now. Most modern technology uses that. It's still destructive, but it's much less so. So it still produces chlorine that can go up and destroy the ozone, but to a much, much smaller extent. There's a lot of other sources of chemicals that destroy ozone. Fire extinguishers can use halon instead. Coolant can use other types of chemicals. Also, helium-cooled refrigerators use much less electricity than refrigerators that use CFCs or HCFCs. So that's a positive benefit. And try to use pump sprays, so sprays where you are using your hand to pump something, to pump hairspray or water or whatever else you're pumping, instead of an aerosol spray, which has these chemicals that cause the spray to come out nicely but do destroy the ozone. And that's what we can do. Thank you.